Hello everyone. Today I'm going to talk about the fractional version of Hedetniemi's conjecture. So this conjecture is about the coloring the product of graphs. The product of G and H has vertices xy, the pairs xy, such that x is the vertex of G and y is the vertex of H, in which xy is adjacent to x prime y prime if and only if x is adjacent to x prime in G and y is adjacent to y prime in H. Now, Hedetniemi conjectured in 1966 that for every graph G and H, the chromatic number of the product graph equals the minimum of the chromatic number of these two graphs. It was conjectured in 1966, so more than half a century ago, and this conjecture is very well known and attracted a lot of attention. And it turns out that it is not true. In 2019, last year, Shitov disproved this conjecture. Okay, it's very surprising to me. And although this conjecture is not true, I proved in 2011 the fractional version is true, which means that for every graphs G and H, the fractional chromatic number of the product of these two graphs equals the minimum of the fractional chromatic number of these two graphs. Okay, now I first define the fractional chromatic number of a graph. We use Ig to denote the set of all independent sets of G. A fractional coloring of the graph G is assignment which assigns to each independent set a weight. This is a non-negative weight, such that for every vertex, the sum of the weights of those independent sets containing X is at least 1. Okay? Such a mapping, such assignment of weight to the independent sets is called the fractional coloring of G. The weight of such a fractional coloring is just the weight of all the independent sets, the summation of the weight of all independent sets. And the fractional chromatic number is the minimum of the weight of a fractional coloring of G. So this is a definition of the fractional chromatic number of G. Note that if here, instead of the interval 0, 1, we assign weight to 0 or 1. So that means the weight of each independent set is either 0 or 1. Now what is such mapping? Such a mapping is actually a selection of independent sets. Those independent sets that map to 1 are selected, and those mapped to 0 are not selected. Okay? With this interpretation, this means that if this inequality is satisfied, that means every vertex is contained in at least one selected independent set. Okay? So then this is a coloring of G, right? This is a selection of independent sets that covers every vertex of G. And the weight of such a mapping is just number of selected independent sets. Okay, so if you minimize the number of independent sets that covers all the vertices of G, what you got the chromatic number of G. So that is why if here instead of 0, 1 we put the interval 0 and 1, this becomes the fractional chromatic number. So each independent set, it's not maybe half selected or quarter selected, so it's fractional. Okay, if I is independent set of G and we take the product of I with the vertex set of H, so this is a set of pairs. The first coordinate comes from I, the second coordinate is an arbitrary vertex of H. This is a subset of the product graph of vertices of the product graph, and it's independent set. You take two vertices from this set. The first coordinate came from I, so they are not adjacent. You remember that for two vertices in the product to be adjacent, both coordinates has to be adjacent. So this is independent set. Now if phi is a fractional coloring of G, then we can lift it up to a fractional coloring of the product graph. Just assign the weight of this independent set to this independent set. It is easy to say that this is indeed a fractional coloring. That means for every vertex of the product graph, the weight, the sum of the weights of those independent sets containing that vertex is at least 1. And the total weight, so this assignment, that means that for other independent sets, the weight we assign to 0 to other independent sets. Okay, the total weight of this fractional coloring is the same as this fractional coloring. So this shows that the fractional chromatic number of the product graph is bounded by the fractional chromatic number of this graph. And similarly, it's bounded by the fractional chromatic number of H. Therefore, it's bounded by the minimum of the fractional chromatic number of these two graphs. Okay, so we want to prove that equality holds, and as we have seen that the last way equal already holds, to prove the equality we just need to prove the inequality of the other direction. Okay, so I'm going to use this duality in linear programming to prove this. So what is the fractional chromatic number? The fractional chromatic number is the solution of this linear programming problem. So this is a linear programming problem. Okay, this fi, these variables has to be positive, non-negative, and they have to satisfy this constraint. This is a linear constraint. And this is a linear programming problem, and the dual problem defines a fractional clique number of G. Now, what is the dual? The dual is that you assign weight to each vertex of this graph, so that the constraint is for every independent set, the weight of that independent set, that means the summation of the weight of the vertices in that independent set, is at most 1. And then you try to maximize these variables, these weights of all the vertices. This is the dual of this linear programming. And this defines the fractional clique number of G, which is denoted by omega fg. Okay, so if this is assigned weight from the interval 0, 1, if instead of the interval where the weight of each vertex is either 0 or 1, then what is that? That is a selection of vertices of G, right? Those vertices mapped to 1 are selected, those vertices mapped to 0 are not selected. Then what is this constraint? This constraint says that each independent set contains at most 1 selected vertex. That simply says that the selected vertices form a clique. Right? And what is this? This is the number of selected vertices. Right? If you maximize this number of selected vertices so that the selected vertices form a clique, what is that? That is the clique number, right? So that is why it is called fractional clique number, because each vertex need not be selected or non-selected. It could be half selected or quarter selected. Okay, so that's the fractional clique number. It's a very important concept for this proof. We review this fractional clique number again. What is a fractional clique? Assign weights to the vertices, non-negative weights to vertices of G, so that for every independent set, the total weight is at most 1. The weight of each independent set is at most 1. So that is a fractional clique. Okay, and the weight of the fractional clique is the weight of all the vertices, and the fractional clique number is the maximum weight of a fractional clique. Okay, so by the duality in linear programming, so these two problems are due to each other, so they have the same solution. That means for every graph, the fractional clique number equals its fractional chromatic number. So this inequality is equivalent to this, right? Instead of proving this inequality, we're going to prove this one. Somehow this is easier in some sense, because to prove this, we just need to find one fractional clique of this weight, because the fractional clique number of this is the maximum weight of fractional clique. So if we find one fractional clique of this weight, then we are done. Okay. If you want to prove this directly, then because the fractional chromatic number is the minimum weight of a fractional coloring, so you have to prove every fractional coloring have weight at most this much. Okay, that's a difficult thing in some sense. Okay, so we're going to construct a fractional clique of the product graph with the given weight. So we take a fractional clique of G of maximum weight and the fractional clique of H of maximum weight. This G is a fractional clique of this graph of maximum weight, and H is a fractional clique of this graph of maximum weight. Then we define phi xy to be this. Say phi xy is gx times hy divided by this number. Okay. So xy is a pair, and this is a vertex of the product graph. So phi is a weight assignment to the vertices of the product graph. Okay. So and this weight is non-negative. Right? Of course, it's easy to say it's less or equal to 1, but that's not important. The important part is non-negative. Okay, so each vertex gets a weight. It's a weight assignment. And we're going to show that actually this is what we're looking for. Phi is a fractional clique of the product graph of weight, which is the minimum of this fractional clique number of these two graphs. Okay, so let's first calculate what is the weight of this weight assignment. So the weight of this is just summation of the weight of all the vertices, and plug in this formula, and then sum separately. First sum according to y, and then sum along x. So this is a constant, we take it out. Then the summation of these is just the fractional clique number of h. Summation of these is the fractional clique number of g. So what do we got these, and the product, this product divided by the maximum of these two, what you get is the minimum. Okay? So the weight of this assignment is correct. It is equal to the minimum of the weight of the fractional clique number of g and the fractional clique number of h. So it remains to show that phi is indeed the fractional coloring. That means that for every independent set I of the product graph, the total weight is at most 1. Okay, so this is, we still have to prove this one. This is the difficult part. This is for every independent set. Okay, so we need to show that total weight is at most 1. Okay, and so this is the formula for this phi xy. Now it's a little bit complicated because they have divide by this maximum. For convenience, we're going to that wxy just equals gx times hy, which is just proportional to xy, equals xy, phi xy multiply this number. So then for a subset u, which is the weight of this u is just the summation of the weight of vertices in u. And what we need to do, we need to show that for any independent set of this product graph, the weight of u is bounded by this number. This is equivalent to that phi u is less or equal to 1, right? Because this equality, so this is equivalent. Okay, so this just for convenience, we just do not have divide this number each time. Okay. Okay, so let's do it. We want to prove that inequality. So this is a vertex. This is the product graph. So this is a G, copy of G. This is a copy of H, and this is the product vertices. These are the vertices of G. These are the vertices of H. These are the vertices of the product graph. Okay, and if you take a vertex of G, take a vertex of H, and then the corresponding this is pair xy. That's a vertex of the product graph. The weight of this vertex is this. Okay, and we want to show every independent set weight is bounded by this number. We may assume that this maximum equals this one. So this is the maximum one. This is again just for convenience. We do not have to write the maximum of this. We just assume this is the maximum. Okay, now. So let's review these are the vertices of the product graph, and what are the edges? The edges are in this formed in this way. You take an edge of G, take an edge of H, and then you get two edges in the product. Right? So this is adjacent to these because their first coordinate is adjacent, and the second coordinate is also adjacent. So each edge of the product graph came in this way. Okay, we take an arbitrary independent set of the product graph. Say the red dots is form an independent set U in this product graph. First, we're going to define a partition of the U into two sets, A union B. This is disjoint union. Now, what is B? B is defined as follows. Say this vertex, this is a vertex of U. I put it into B. If this happens, what happens? If like this is x, this is y, this is the vertex xy. I put it into B. If I can say find another, look at the column that is in the y column of this picture. If I can find another vertex also in U, but if I look to the first coordinates, there's an edge between these two vertices in G. Okay, so you find x prime, x prime is an edge of G, and x prime y is also in U. That is, in that case, I put this vertex in B. Of course, this is also put into B. And say the remaining vertices I put into A. So suppose these are the vertices in B and the remaining vertices in A. So this is a partition of U into A and B. Okay. So you look at each vertex of y. You look at AY, and what is AY? AY is just look at this column. Okay, look at those vertices I put into A. I look at those vertices into put A. So this one, this is into A. This is in A. This is in A. Right? And in this one, say this is in A. This is in A. Then I look at the first coordinates. So this is AY. The first coordinate, it's a subset. AY is a subset of G, of the vertices of G. Okay, it's convenient to think of, say, each column is a copy of G. In that case, each column is just a look at those vertices. But these two vertices regarded as vertices in G. By just looking at its first coordinates. Okay? In this sense, so this is my AY, but actually I should look at here. Okay? This is copy of G. It's convenient to think that way sometimes. Okay, so now each AY is an independent set. You look at here, this is AY, this is independent. Why is that? If there's an edge here, if there's an edge between, say, you look at this, if there's an edge between these two vertices in G, by definition, I should have put both vertices into B, right? So by definition, this is an independent set. And then I look at each vertex X and look at the row indexed by X. So I look at those which put into B. So again, each row I can view as each row as a copy of H. Okay? Just look at the second coordinate of the vertices in this row. Okay? So in this sense, these are the vertices in Bx. You look at X and go through this row. Okay? And this is a subset of vertices of H. And this is an independent set in H. Why is that? Okay, suppose this is not true. That means let's look at this X. Look at this X. As I have these and this vertex in Bx. This in Bx. I should look at the first coordinate. Okay, this in Bx. Suppose this is not independent. That means I look at the second coordinate. There's an H between them. Okay, and then I look at this vertex. Why do I put this vertex into B? This vertex into B because I find this vertex in U, and look at here. There's an H. That's the reason. That's the reason I put this vertex into B. Right? Then you look at the product of this H and this H. You should have this H here. So, but this is a contradiction because both vertices are in U, which is independent set. This H is in the product graph, right? But this is U is independent set in the product graph. So that's a contradiction. So this proves that Bx is independent set of H. Okay, so this is what we're trying to prove. For every independent set U of the product graph, and we want the weight of the of this set, independent set, is bounded by the fractional clique number of G. Okay, this is what we want to prove. Okay, so let's write down the summation, and because U is partitioned into A and B, so the weight of U is the sum of the weight of A and the sum of B. Okay, for this one, I first fix Y and sum up among all those X, such that XY belongs to A, and that means I sum up among all those GAY, and then I sum along these Y's. Similarly, I first fix X and sum along these Y's, I get this, and then sum along this vertices X. Okay, now I'm going to estimate this value. What is this? So this is G and this is G. This is AY. AY is an independent set of G. Okay, I'm going to calculate the weight of this part under this weight assignment G. G is a fractional clique of G. Okay, I take this close neighborhood of this independent set, this including the independent set and all their neighbors. Okay, so I claim the weight of this part is going to be bounded by the weight of the big part divided by the fractional clique number of G. This is a claim. I'm going to prove it. Once I prove this, I'm going to plug this in here. Okay, so let's prove this first. Look at this subgraph. This is the subgraph induced by the remaining vertices. If there's I take an independent set from here, take an independent set from this subgraph. This is independent. This is independent. There's no edge between them. So the union is independent set of G. The union is independent set of G. And therefore, because G is a fractional clique of G, so the weight of this union is bounded by 1. Okay, this means that GAY prime is bounded by this number. Now, if I define G prime X to be this number, then what I get is that for every independent set of this graph, every independent set Y prime of this graph, G prime Y prime is less or equal to 1, right? Is this number divided by this number, so it's less or equal to 1. That means G prime is a fractional clique of this graph. But this is a subgraph of G, so the fractional clique number of this graph is bounded by the fractional clique number of G. So that means the sum of the weight of this function, okay, among all the vertices here, that's all the vertices here, is bounded by the fractional clique number of G. Okay, so now this is for this summation, this is a constant. I multiply to this side and then sum up the weight of X, what I get. So on the right hand side, this is 1 times this, and this is GAY times this. So the right hand side is this. The left hand side is the summation of GX to these vertices. So that means the summation, the weight of all the vertices in G, that is the fractional clique of G, minus the weight of this set. Okay, and if you cancel this fractional clique number of G from both sides, I get this inequality. Okay, and if you divide both sides by this fractional clique number of G, this is the claim I written here. So this claim is proved. Okay, I proved this claim. Then plug in here. So this summation of this is bounded by this divided by this, by the fractional clique number of G. Okay, so this is less or equal to this, and similarly this one is less or equal to this one. Okay, and if I change this to fractional clique number of H, so fractional clique number of H is less or equal to the fractional clique number of G. That's by assumption. So this becomes a big number, so the right hand side becomes bigger, so the inequality still holds. Okay, so now we have this inequality here. We have this inequality here. Okay, so now this is AY and this is BX. and this is the close neighborhood of AY, and this is the close neighborhood of BX. Okay, when I put this, so when I say look at the close neighborhood of AY, I treat this column as a copy of G. Just look at the first coordinates. When I say the close neighborhood of BX, I treat this row as a copy of H. Okay? But actually, it's the second coordinate is a copy of H. This is the first. When I look at the column, look at the first coordinates, look at the row, look at the second coordinate. Okay, now for each row, for each column, I take the close neighborhood of AY, and for each row, I take the close neighborhood of BX. Okay, so that's. Okay, so now let's look at the this is summation. Let's concentrate on a particular y, that's fixed y. Say this is this column, fix this column, and look at the summation of this. What is this? So this is the weight of these vertices. You look at the first coordinate. You have to go to the. This is you think of this as vertices of G. Okay, the weight of these vertices in G, then multiply the weight of Y. This is the column, and then sum them up. What is this? This is actually the weight of these vertices in the product graph. Okay, so each vertex, the weight is gx times hy. So you multiply gx times hy, you sum up all these, you got this one. Okay, so this means that what is this summation? This summation is actually this part is just the weight of those vertices, the weight of the vertices in the product graph, the yellow area, and this is the summation of the weight of the vertices in the blue area. So then there's a very important critical claim here. That means that is the yellow area and the blue area do not intersect. Okay, so I draw this picture here, so they do not intersect. There's no vertex which belong both to the. There's no vertex which is both blue and yellow. But why not? Why not? The claim says yes, there is no such a vertex, but it needs a proof. It's a critical fact that needs a proof. Okay, so let's assume there's some vertex which is both yellow and the blue and the yellow. Say for example, so this vertex is both yellow and blue. So what it means like this. Okay, this vertex is not in AY, but it's in the close neighborhood of AY. It's not in BX, but it's in the close neighborhood of BX. Okay, then why this is in the close neighborhood of BX? That means I can find the vertex in BX and then look at the second coordinate. There's an edge. There's an edge. Now, why this is in the close neighborhood of AY? That means I can find the vertex in AY, and you go to look at the first coordinate. There's an edge, but then there should be an edge between these two vertices in a product graph. That's a contradiction because these two vertices both belong to U, which is independent set. Okay, so there's no such a vertex like this. And another case is that maybe so there's a vertex which is in AY, and if it's in AY, then of course it's not in BX because AB are disjoint. But it is in the close neighborhood of BX, say like this. Well, if this is the case, then I ask, this is in B, so why are you in B? Because this is the definition of, I put it in B. If we go this column, I can find a lot of vertex in U such that you go to the first coordinate, they are adjacent. This is the reason I put these vertices in B. Okay, now you said that this is in the close neighborhood of this vertex. That means there's an edge between, you go to this second coordinate, there's an edge between this vertex and this vertex. Okay, then I should have an edge between these two vertices in the product graph. That's a contradiction because these two vertices are in the independent set U, both in the independent set U. Okay, so this proves that there's another case that is, for example, say this vertex in it is in Bx, and maybe it is in a close neighborhood of, say, this becomes yellow, so it's close. It's the same contradiction. I will omit that case. In any case, that we prove this claim: the yellow area and the blue area do not intersect. Now we go back to this summation. We know that this is equal to the summation of the weight of the vertices in the yellow area and the blue area. But the yellow and the blue, they do not intersect. That means this is bounded by the summation of weight of all the vertices. Right? If we sum among all the vertices, what I get is first sum up among all these y's, I get the fractional clique number of h, and then sum around x, I got the fractional clique number of g. And so this is, and the cancel these, I got the fractional clique number of g. So this is the maximum amount of this fractional clique number of g and the fractional clique number of h. This is what we want to prove. Okay, this finishes the proof. It's the end. Thank you.